So let's look at the second type of transfer learning, which is actually also quite intuitive. It's so what do we do in the second version? It's basically fine tuning, and fine tuning, as the name implies, is saying that we had this pre-trained network with all the weights already decided, and what we're going to do is previously we were not changing anything about the weights. It essentially was being used to transform an image to a vector. Now what we're going to do is do an end-to-end update of these weights, in the sense that we'll actually use, it's like initializing my network with these weights. Of course, then the network has to be the same structure, exactly the same structure, except the last layer still, if I have a 2-class classification and ImageNet has 1000 class classification, I have to drop the final layer and connect a new weight matrix, which will be 4096 cross 2, like whatever is the number of classes. The number of scores determines the last weight matrix's number of rows, right? So the last layer, we just change it to a different weight matrix. Because it's fully connected, it's just going to be some W matrix where the number of rows is 2 and the number of columns is for example 1000, right? And then we have all these other weights. Okay, we'll train our neural network, which we'll backpropagate. We have our data, which is which may be 2 classes, houses versus something else like stadiums, and we have these 100 images of each class. Then we're gonna do the usual backpropagation. We have cross entropy loss. We'll pass an image of a house. We'll look at the score with respect to house, with score with respect to a stadium, and we'll try to maximize the score with respect to the house, right? So that's how cross entropy loss will work. But we'll backpropagate the gradients. We'll update the weights of all the weights, pretty much. I mean, it doesn't have to be all the weights, but we'll also update the weights of the pre-trained network. Okay, so that's I guess this slide is trying to show that let's say this was our pre-trained network. We can drop a couple of fully connected networks. I mean, it doesn't have to be 1 or 2, but let's say I drop 2 of them. Then I'll reintroduce 2 new fully connected networks, fully connected layers. Sorry, it doesn't have to be 2. It can be just 1. For example, it could be just the last layer. Okay. And then I'm gonna, so this will correspond to some weight matrix, this will correspond to some weight matrix, maybe W1 and W2 matrices. But there will also be weights. I mean, filter weights correspond to this guy, filter weights correspond to this guy, filter weights correspond to this guy, right? Those weights were captured from the pre-trained network, like VGG or AlexNet or ResNet. Okay. Now we will backprop. So we'll backprop. What does backprop do? Update the weights. W1 and W2 anyway we have to update. We initialize with some random numbers. But we'll also try to update the weights of these con layer filters, that con layer filters, and that con layer filters. But we'll update them in a fine manner, in the sense that the learning rates, the way we update is usually by gradient based update, right? So the current weight is subtracted. So we subtract a learning rate times the gradient of the loss with respect to the current weight and update to the next weight, right? Remember, this was something like f3 at time t plus 1 is f3 at time t minus some alpha times gradient of the loss with respect to that f3. Or, like think of that as a single number, for example. Then I'm just saying that by fine tuning, I just mean that this alpha, which controls how much I update these weights, is going to be extremely low, like 10 to the power minus 5 or 10 to the power minus 7, like really small nudges to the weights. And what's the idea? The idea is that if it's a pre-trained network on a similar type of domain, for example, you're trying to classify houses versus stadium, but ImageNet has so many different classes, like dogs, cats, other animals, various other things, cars, and so on. But it still had something to do with houses, something to do with stadia, outdoors. Okay. The lower level layers capture some common elements among these types of domains. Okay. So that's why we are retaining the lower layers, and that was the intuition for also using them as feature extractors in the previous version. In the previous version, when I was passing an image and getting this 1000-dimensional vector, and I said it could still work really well and give you a high classification error, the whole premise was that that lower level layers, not just the lower layers, but all these layers which are trained on the domain of houses, cats, dogs, other animal breeds, and so on, can pick up those neurons. Those weights are such that the neurons can pick up signals of natural images. Okay, and hopefully your classification task has to pick up similar patterns while classifying your in your classification task. Okay, and here by fine tuning we are saying that okay, we already are quite good, we are quite happy with the pre-trained networks weights, but we'll slightly change them to further improve or slightly reorient the weights such that it picks up the even better signals for my classification task. Okay, and as I said before, the R task doesn't have to have thousands of images. It can just be a few hundred. In fact, it could be as low as like 30 images or 10 images per class. Okay, you'll still be able to gain value, and this is just transfer. There has to be some relation between the pre-trained network and the task you're doing. For example, if your task is about medical image classification, whether there's a whether the input is an image of certain type. For example, certain types of medical images have 4 dimensions, not 3 dimensions. Okay, first of all, but even if you had 3 dimensions, it could be which could have very different spatial patterns. Think of something like an X-ray or an MRI, which is reduced to 3 dimensions. It will not have the same type of spatial patterns, but the ImageNet pre-trained network would have trained on, so it will not work typically. Okay, or images of the sky, for example. You're trying to detect whether a star exists or an asteroid exists or something like that. It will not potentially work. Okay, any questions about this part? Okay, yeah, and this is a little bit older. This is from 2014. So somebody kind of looked at what was the previous existing pipeline for doing anything to do with images, right? So this was a pipeline. You had an image. You would somebody would annotate different parts of the image, and there are these hand engineered feature engineering tricks that go in there, something called deformable parts model and so on. And ultimately there's an SVM. So what I'm trying to say is this: all these green blocks were essentially some feature engineering. Okay, and then you had an SVM classifier which would classify to a particular class. You could actually, so this was the thing that was doing ImageNet classification of 1,000 classes back in 2011. Okay, so we were actually doing SVM classification, but with a lot of feature engineering such that SVM could do really well for 1,000 class classification. But then now you can have a CNN based representation, and you can actually, whatever pre-trained network is there, you can actually use it for many different problems. So here on the x-axis they're showing different types of problems. For example, object classification is the original ImageNet classification. Okay, that's an ImageNet problem, one of the ImageNet problems, where you just have to detect a single object in an image and detect whether classify that single object in that image to be of certain class, like a dog, a house, or something like that. Okay, but there are many other image recognition, image based problems. Okay, for example, retrieval of related images, things like bird subcategorization and so on. So these are related tasks, and they were showing that you don't have to retrain every time from scratch. You can actually use that pre-trained network and actually beat in terms of performance numbers here. Beat in terms of the performance numbers compared to running everything from scratch for each task. Okay.
So best testers of the art means everything other than CNN?
No, best state of the art means it's the what is the best state of the art. So it could be a CNN based model as well. So here they are just trying to illustrate that I just download some pre-trained network, and with some moderate amount of like fine tuning and so on, I can get to almost the best. So you may not be able to get the same number, but okay, CNN based methods, some of them are anyway beating the best of state of the art anyway. So okay, the point of the slide is saying that you can really do really well across tasks by just using transfer learning. And this was back in 2014, and this idea has kind of resurfaced again now in 2019. It's pretty much all packages like PyTorch, TensorFlow give you already pre-trained networks, and they pretty much achieve really good state of the art. Like if you use those networks, for example, for a Kaggle competition, okay, you will never train something from scratch in for example, a Kaggle competition. Yeah, so somebody was asking like what were the labels. When I keep on referring to ImageNet problem. So it falls under this thing which is the vanilla classification problem. Okay, it's basically I guess in the computer vision parlance it's just called the object classification problem. Okay, you have a single object in the image and you just want to classify it as one of the 1,000 classes. Okay, but there are other problems like classify and localize. So your output is not just which class it belongs to, but also where is that object. Okay, it's in this example it's in the center, but what if the cat was at the top right corner? You still have to identify that it's a cat and it's in the top right corner. Okay, and of course your training data needs to have annotated images where somebody has painstakingly drawn where the image is in where the object is in the image. Okay, somebody has done it, and given that type of training data, you can do this localization. You can solve this localization problem, and you can do this using neural networks. We may get to this maybe in a later lecture. Okay, how to do this? It looks like we are producing a box and a class, so it's a little bit non-standard output. Similarly, object detection means you can detect multiple objects in the image as well as the bounding boxes across them. Okay, it's like it's not just like multi-label classification where given input image, for example, you can say there's a dog, cat, and something else. Here you're saying there's a dog, cat, and something else, but where exactly are they? Okay, so you put bounding boxes on. It's a harder problem than I guess just localization of a single object. And then segmentation is a problem where every pixel is classified. Every pixel in the input image is classified as whether it belongs to a cat class, whether it belongs to a dog class, or whether it belongs to the background class, for example. Okay, so it's like a even more complicated classification problem essentially. Okay. But somebody for note that for this type of task, it's not that the input data is still just image and a class label. For this, for example, your input image should have a segmented. So your training data will have an image and every pixel classified to be something or the other in your training data. Okay, given that type of training data, you can do this as a task. Okay, so yeah. Any questions about transfer learning? I mean they're pretty straightforward. The two types of transfer learning that we saw. Okay. So now let's look at. So I call this neural net training tricks, but actually they are kind of important. So we'll basically what I want to do in the next few minutes is to look at basically 4 things: data augmentation, weight initialization, batch normalization, and dropout. Okay, there are four words that I threw out here. I'll tell you what each one means, and each one has an impact, especially for images, on classification accuracy. Okay, and of course other tasks as well. But let's understand what's happening. So yeah. So what is the first task? First, not first task, but what is the first trick? Okay, first trick is the idea of augmenting data. Images are quite natural. We can process them very quickly. We don't think of them as numbers with 3 layers and so on. So the idea is precisely that images can be transformed in certain ways, and it still has to belong to the same class. Okay, which is what I repeated a few minutes ago. That if the cat is in the center or is the top right, you still should say cat. So in your training data, okay, if you had a cat in the center and the class is cat, you can actually augment your data by creating additional images where you keep shifting the cat left and right and top and bottom and still say that the class is cat. Okay, so it's like saying I had one data observation which is a cat image and its class. With that, I have created 10 images or 100 images of again cat shifted all over the place, rotated all over the place, and maybe and still say class, still say cat. Okay, now I've just augmented my data. I have not touched anything about training or anything like that. I've just increased my data size. Okay, of course you don't want to do this offline in the sense that let's say I have 1 gigabyte of images. Okay, maybe 10,000 images per class, maybe 100 classes. I will not, if I put up each image this way and create 100 copies of it, then I'm going to explode in terms of storage space. So we can actually do it on the fly. Okay, so on the fly just means that when you pass this observation point into your network and do that forward pass and back propagation, just at that time just do this perturbation of your input, translate, rotate, whatever, and then do the forward pass. Okay, so that's all it means. So in terms of observation, xi just got transformed to x tilde I, where x tilde I is a transformation, and here are some transformations. Change the color, flip across the vertical axis, crop randomly, and scale randomly, and again I guess those two are crops. Okay, so, and in fact these are written, for example, in PyTorch. There are these transformations which are predetermined. You have to just pass appropriate parameters. Okay, we'll see. Actually, I'm not sure, there was a CNN walkthrough script from PyTorch tutorials last time. It is on the syllabus page, which I mentioned, right? It's under the lecture 2's materials. Maybe if we have time, we can go through that, and there will be some transformation like this. Okay. Yeah. So at test time, so you can do these transformations for training data, right? To learn the parameters. But you've learned the parameters, let's say. Now, what do you do with at a test time? At test time, you have a single image. You want to find its label. Even that image, you can actually do cropping as well. Okay, you can say, you can classify. So it's like saying, I have that image. Let me classify it using my training data. Maybe it says cat. Maybe it says dog. I crop it and then again push it through the network and ask the network what's the class. Maybe it says cat this time. You can always take a majority vote. Okay, in the sense that you have an input image which you want to classify at test time. You can always do transformations on it and ask every time what did it classify it as. Sometimes it may misclassify, but hopefully majority of the time it will classify it as the right class. Okay. So there's a particular example of these guys, but that's not very important. You can actually do transformations even at the test time and get a bunch of classifications and look at the majority classification. Right? So, but image space, it's kind of easy to intuit about this, because images, you do a slight translation, rotation, and so on. It hopefully is the same class, but it's not clear how to do it with tabular data, for example. Like you have tabular data with age as one column and something else, demographic information in other columns. It's not clear how you perturb and say whether it's it's the same class, right? It's not clear. Yeah, it's fine. Okay, so that was data augmentation. So next we're going to look at a few things about the model, and what have we seen so far in the modeling part. We have seen non-linearities, right? We have said let's use ReLU, and there were other non-linearities, but we did not focus on it because ReLU seems to get us really good accuracy anyway. If you want to kind of experiment with other non-linearities, you can do that as well. And we also saw, okay, number of layers and number of neurons per layer influence how well my model works. In fact, there is this script from TensorFlow's tutorial page called overfit and underfit. Okay, I just got it earlier, a few hours ago, and it's basically trying to illustrate. Okay, pictures. Yeah, it's trying to illustrate what is the impact of, for example, okay, let me just minimize this. Yeah. Okay. So it's just trying to illustrate, this choice of number of neurons and number of layers. Some people have asked me this question offline as well. Like, how do I decide, whether should I choose the number of layers first, or should I increase the number of neurons first? It's not clear. So here they're trying to kind of, at least, one variation of this is that they're trying to see whether a smaller network works or a larger network works. What's the difference between those two? Okay, and like for example, here you can see that like there are three networks. So there's a baseline. Okay, the orange one is the smaller network. So this is the smaller one, and the green is the bigger one. Okay, this is the bigger one. Okay, B for bigger and S for small, and there is some baseline network. Okay, the baseline network I think is just some logistic regression model with some, let's say it's logistic regression. I don't recollect what exactly it is. They're trying to show two curves. Okay, so x-axis is showing epochs, or number of times you pass data forward and get upgrade and update and get new parameters. Okay, and y-axis is showing binary cross entropy loss value, and of course loss value means lower the better, and they're showing the solid curves are showing training error. Okay, so training error, of course, it's fitting the data better and better as you update the parameters more and more. In fact, you actually have zero error for the green guy, which is the biggest network, bigger network. Okay, so you have overfit, you've pretty much got zero training error, zero, I guess, cross entropy loss value for the biggest network. For the other two networks also, if you train more and more, you're able to fit pretty much you're pretty much able to fit, almost able to classify everything correctly. Okay, I think this classification task is some sort of I think IMDb sentiment classification problem here, but that's not very critical. So what I'm saying is these are the performance in the training, and in terms of test, which is the validation error, they are also plotting the validation error here. You can see that the smaller network has the lowest validation error. It's still going up as you increase the number of epochs. So it tells us that, first of all, the network size, bigger is not always better, right? Biggest network is actually doing worse, right? But even the smallest network is also going to do worse as you increase the number of epochs. Okay, maybe you should have stopped, in 5 epochs. Okay, so there is this also the number of times you're using the same data to fit your network. Essentially, that's the epoch indexing, right? And also the size of the network matters. So they're not really discussing at the level of number of neurons and number of hidden layers, but yeah, actually in this experiment, it's actually the number of neurons that's changing. So the number of layers is the same. I'll share the script with you after this class, but it's basically a 3-layer neural network, 3 dense layers, nothing convolutional here, and they're just changing the number of neurons in the number of neurons in each hidden layer. Okay, the biggest network has 512 neurons, and the smallest one has like 4 neurons or something. There's some difference. Okay. Anyway, so that was a tangent. And then there were some filter choices, like what is the size of the filter, what is the stride, should I pad around the border, and so on. They all are interesting considerations. I mean, mostly striding and padding are about, like, do you want to pick up fine-grained patterns, or do you want to pick up patterns at the borders or the edges and so on. Okay, borders or edges of the input tensor. If it's an input image, if there are some patterns in the border, you want to pick it up or not. Okay, so these are what we've already seen. So what we're going to see now is 3 things. Actually, we'll not spend much time on weight initialization, but we'll see 2 other things, 2 other tricks which influence the performance of a CNN or a feed-forward network. Okay. Any questions about where we're going? Okay, so weight initialization. I just mentioned this when I was talking about these dead ReLUs, or essentially activations never firing, never giving any positive number. If you start with weights being all minus infinity, or not minus infinity, but minus 100 everything, then it's probably, nothing will be trained, because forward pass is all zeros, backward pass is all zeros. Okay. But at the same time, even if you start with W is equal to 0, all zeros, that may also not give you any good gradients. Okay, even if the weights are zeros, your forward pass may reach up to some loss value, because the weights were 0. Maybe biases can help you, maybe, to counteract and give you some positive activations at some layers, but it's not clear. And so people have and so 2 things. One is first one is that first of all, the loss surface. So this is just an illustration for a 1-dimensional problem. Okay, this is a 1D problem, whereas the number of neurons that we have already at a single layer, we saw at the extreme beginning of this lecture, with 5 filters, it was already 500 parameters, right? 500-dimensional problem with just 5 filters. So 50 filters, 5,000 numbers, right? 5,000 dimensions. And if you have 10 such layers, then it's 50,000 dimensional problem. But here, this illustration is just for 1-dimensional problem. 1-dimensional problem, if you have a curve like this, you can see that if I start from here, or if I start from here, if I do gradient descent, I'll reach different valleys and different bottoms of the valleys, right? Different valleys here, or here. Okay, I can imagine how, and it turns out that because of nonlinearities that we introduce, in particular ReLUs, the loss surface in this 50,000 dimensional space is also like this. Okay, it's wiggly all over the place. You can't really imagine it. Okay, because it's like that, where you start matters. So what starting point matters. We cannot actually get to the best best W which gives us the lowest loss ever, because in 50,000 dimensional space it'll take millennia for us to really figure out where exactly is the bottom, the global minima. Okay, so we cannot do that. So that's an open problem, and in the sense it's not clear if we can solve it. uh, and that's why initialization matters, and that's why all these tricks matter. What is the issue with training deep neural networks is this whole loss landscape is highly nonlinear. It's not clear whether it has a nice structure. In multi-class logistic regression, the loss surface is actually like this, like a parabola. It's like a ball, even in one dimension, whether it's 1,000 dimensions. If you just do multi-class logistic regression, which is no hidden layers, just a softmax operation, it's a nice ball. So you'll know that you will get to the bottom, by doing gradient descent. The moment you introduce hidden layers, it's not the case, and that's why we are doing all these tricks. Okay, CNNs and convolution layers or max pools and all that to somehow deal with the dimensionality as well as deal with getting to good value values. Yeah. And the second point is, I guess that's the first point, is that this is a horribly hard problem to optimize neural networks anyway. A second point is people have figured out some heuristics to initialize Ws. There's things like low-rot initialization and so on, but let's not worry about it. It's just like picking a random number uniformly at random between two numbers. Okay, it's like saying I initialize my Ws by randomly drawing it from -1 to 1. Okay, that will be my W value for each weight or each filter that I want. It's random initialization, but there are certain people have figured out that maybe the support of the random variable should not be between -1 and 1, could be between 0.5 and 0.5. -0.5 and 0.5 would be better. So people have experimented with these things. Okay. So that's it. So we'll get back to weight initialization. Actually, the related topic to this is the whole point of optimization, right? The whole point of why SGD, and some of you have tried SGD versus Adam, and somebody wrote Adam Delta or something was the best optimizer or something like that. So you've tried a few optimizers in your first assignment, right? So we'll see how do they work and what are the nuances. How do they counter any of these issues that we see, the major issue that we see here. Okay. Yeah, what was it? Okay, so let's look at batch normalization. So this is a little bit it involves the notion of a batch. Okay, so that's something that we've not seen so far. I mean, we have seen it, but kind of it was not very critical. So what is the motivation for batch normalization? Okay, weight initialization, we said, okay, where you start influences where you get to. Okay, here the point is to control the magnitudes and statistics of the activations themselves. What do I mean by that? You have let's say 1,000 images. Think of a single neuron. Each of the image activates it by a little bit, right? Either it is 0 or non-zero. If it's non-zero, it's some value. Okay. If you look at the distribution of 1,000 numbers, it will look like something, right? It will be positive. If it's after the max, after the ReLU nonlinearity, it will be some numbers. Histogram, you can look at the histogram, right? The point of batch normalization is to somehow skew these activation values to look like a normally distributed statistics. Okay, just somehow skew these histograms, and there's no trick here. Literally, they subtract the mean and slightly divide by some number so that it looks like a zero-centered a bunch of activations. Okay, before it's passed to the next layer. Okay, so how do you do that? You can't do that for a single image. So there's this notion of batch that we'll get to. Okay, and that's how we'll control the activation statistics. So we'll recenter and so on. And if we can control them, so activations will not go to, remember ReLU is like this, right? So if activations are, if activation magnitudes are high, then although the local gradient is unit value, the gradients can explode in the sense that they can get multiplied. If they're large numbers greater than 1, if they multiply together, when they backdrop all the way to the w, they can keep on increasing, right? They can go up to infinity, not infinity, but they can increase magnitude. Or or if they're smaller than 1, they can kind of if the number of layers is too deep, then 0.9 times 0.9 times 0.9, it goes down to 0 very quickly. Okay, so there's this issue of controlling the activation magnitudes and so on. So that's why there's this essentially some sort of a normalization happening. Okay, and of course the local so the activations also can be part of the gradient values themselves. Okay, but this is a minor point. So let's see. So what is batch normalization? Okay, so for that we need to have the notion of a batch. So let's say we have a batch size of n. So n, let's say, is 10 images. Okay, so we have 10 images. Now what we're going to do is think of a fully connected layer. Okay, so I have 10 images. Each image, let's say, is 100 dimensional. Let's say 10 cross 10, no RGB. Let's say simple 10 cross 10 matrix is the image size. I just vectorized it because in a fully connected network there's no notion of image, a spatial aspect and so on. So 100 dimensional fully connected network. Let's say it outputs let's say, again I'm using 10 too much. So let's say it outputs a 15 dimensional vector. Okay, think of the simplest. Think of the first day's neural network, feed-forward neural network. We had this 2-dimensional data which was going to some 100 dimensions or something like that, hidden layers, right? So here I'm saying there's a 100-dimensional input going to 15 dimensions in the hidden layer, something, right? So what we're going to do is actually compute these activations for 10 images together. Okay, and that's going to be, I'll stack the activations which are 15 dimensional. So all I'm saying is this D is 15, let's say. Then I'll stack the 15 numbers that I get for each image. I'll have 10 images, so 10 times 15 dimensional vector, 10 times 15 dimensional matrix is the way I'll think about it. Okay, it's like saying, instead of passing in a single image, if I pass a single image, I'll get a 15 dimensional vector. If I pass 99 other images in addition to that one, I'll get 15 dimensional vector, and sorry, not 99, 9 other images, then I'll get 15 dimensional vector, 10 of them, right? So let me stack them together as a matrix. Okay, that's the blue thing on the right side, the left side, and that's a matrix. So what I'm going to do is just the usual, is going to be per column I'm going to renormalize the bunch of numbers. So think of this as I pass it through a fully connected network. I got a bunch of numbers. These are activations, right? I got one number per image. There are 10 images in this example. So I have 10 numbers. I'm going to renormalize them. How do I renormalize them? I'm going to renormalize them with respect to each other. So I'm going to compute their average value and compute their variance. Okay. So I have 10 numbers. I can always compute the average value, add them up and divide by 10. You can compute the variance as well. I know the average, so I can subtract from the average, take the square, divide by 10 again. And then what I'm going to do is change the vector. So this vector, this 10-dimensional vector, this is the original 10-dimensional vector. I'm going to change it by subtracting the mean and dividing by the variance and multiplying by a number gamma and adding a number beta. So don't worry about these gamma and beta. Let's say it's 1 and 0 for simplicity. That's not very critical. But all I'm doing is that I have a column of numbers. I'm just subtracting the mean value from them and dividing by some other number. Okay, but these numbers are derived from the values that they actually took. That's all. It's just normals. And batch normalization, because I need the batch to actually get these mean values and the denominator. Okay. So what this does is that initially whatever numbers I had here, right? I got new bunch of numbers here, okay, if all these numbers on the left side, let's say, were all positive, then the numbers on the right side, x hats, some of them will be negative because I'm subtracting the mean, right? Somehow recentering, okay, and people have observed that this recentering and renormalization doesn't, helps the stability of passing the gradients back and forth and ensuring that the training works. Otherwise, you'll get gradients saturating, okay, going to positive, very high numbers, or gradients going to 0, and then things not working at all. Training doesn't work, okay. So this is an engineering trick to kind of somehow manipulate the activations, okay, transform the activations, okay. And that's it. That's batch normalization. And here I've shown you a matrix, so you do that for every column, okay. But the batch is important per column, and each column is a single output neuron. And you can do this for fully connected network. You can do this for the output of a convolutional network, convolutional layer. It's fine, okay. So let's not connect it back to convolutional layer because just it's besides the point. The point is that you have a batch of images. You renormalize the activations across the batch. That's all, like this. And what is this gamma and beta? You can actually backprop and figure out the best gamma and beta. Okay, you can either set them to be the same, some fixed numbers, or you can backprop and learn them as well. So let's not worry about how backprop is happening, because you can set them to be some fixed nice numbers like 1 and 0 or 1 and 1 and something like that, and be fine with it. Okay. So, and there is some trick that you need to introduce, because at test time you have a single image, then there is no batch normalization that you can do. So you have to use the intermediate activations that you get, subtract the one you use from training data, and so on. So you maintain some sort of numbers that you computed during training. You actually explicitly keep it somewhere. Okay. Where are we? Wow. Okay. So this is how it would look like. So previously we were just talking about con pool, right? So now we'll look at con. So typically people add batch norm before ReLU, because ReLU is already shifting the numbers to positive domain, right? Zeros is clipping from zeros. So people normalize and then pass it through the ReLU. Okay, that's all. That's the only change. Yeah, and empirically we observe that the gradients, so you can actually look at the histograms of gradients as well. Just like you're plotting the loss as a function of loss is a single number, you're plotting it as a function of epochs, right? You can plot 100 different things as a function of epoch. One of them being, what is the magnitudes of the gradients, what are the, how many activations are positive, how many activations did not fire as a function of epochs, and so on. So you can kind of, I guess, intuit whether properly gradients are flowing and things are getting updated and at the right magnitude, and so on. Okay. So that's batch normalization. Okay. I mean, it's available as an option in PyTorch or TensorFlow, so it's not like we will actually write it, but you need to know what's happening. And the last part, again, which is also available as a default option parameter in different layers in TensorFlow and PyTorch, for example, is this idea of dropout. Okay. So what is dropout? So even before getting to what is dropout, on this diagram, okay, I don't know what to do with that. Yeah. So in this overfitting and underfitting experiment, what they did was, okay, let's add L2 regularization. Okay. They said, okay, now we had a huge capacity, so the validation, so a bigger network, the validation error was increasing, right? So so this was the baseline. So this was the baseline, and this was the smaller network, let's say. Okay. So smaller network already had some increasing validation error in the previous picture that I showed you. So all networks had like an increasing validation error as you increase the epochs. Okay. Previously, so they said, okay, let's add L2 now regularization. The regularization we have seen in the first lecture itself, right? The 2 norm regularization, the weights right? They added that, and they see that now the training error is not going to go to 0, because now you're biasing yourself towards certain types of weights rather than the best weights which can minimize the loss. So of course the loss will not be the lowest, right? Because we're still plotting the loss only, not the loss plus the L2 error. Okay. You can see that, so I'll not go back up because I want to show dropout, is that this guy did not really go down too much. Okay, if there is any difference, it's maybe slightly different from the previous plot. Okay, so adding L2 regularization did not really influence the validation error, but they show that if you use dropout of a certain parameter, okay, even for dropout, it did not really influence this number, okay, this validation error. Actually, where is the, oh, actually, so 0.4, okay, so I guess, so if they only added dropout, they see some validation error for the small network. So what they want to show is actually this, that compared to the baseline, you're doing better by adding dropout, and of course compared to the baseline, even L2 regularization, I think, yeah, L2 regularization is doing better. So the whole point of adding regularization is to do better than non-regularization. So you need to do best outside sample, okay? So you're doing better than baseline's outside sample. So compare this to a previous setting. So baseline is here, and this curve, it's around the same region, but you'll see that if you plot this with the L2 regularization or dropout, you'll see that there's some decrease in this this dashed curve. Okay, that's important. That's the only thing which is important for us. Yeah. Anyway, so I thought there would be a dramatic change in dropout. It was not the case, but that's fine. So what is dropout? Okay, so dropout is a way to regularize, which is a little bit non-standard, and it is that the idea is as follows. Okay, during training, every time we do a forward pass, which is that every time we have, we can always pass a batch of my observations rather than each observation and then looking at the gradient with respect to that observation, right? We saw this idea of batching in the first lecture itself. Every time we forward pass, we set the outputs of a few neurons to be 0. So we force the outputs of a few neurons to be 0. Okay. So what is the output of a neuron? That's the activation, right? So think of a layer. There's a convolution layer. It had an input tensor. It processed it and created an output tensor. In those output tensors, I'm going to set some of the numbers to be 0. That's all I'm saying. Okay. So this transformation from the input tensor on the output tensor already had this, batch normalization and ReLU operations already. Got some output tensor. I'm going to set some of the entries to be 0. Why what is the motivation? The motivation is that the network has high capacity. It can learn a lot. It can overfit the data. So by setting the neurons to be 0, those neurons are out of action. They cannot propagate gradients backward. Okay. So it's forcing the rest of the neurons, which are not 0, to learn the pattern in the data to classify the particular image correctly. Okay. It's restricting. It's like saying I'm looking at a smaller neural network than the full neural network. If I'm setting the some neurons to be 0, their outputs to be 0 for this particular data, let's say an input image, then I'm saying that I'll drop these neurons. They are not relevant to my architecture, relevant to my model. Only the rest of the model should somehow guess the class correctly, and if it's not, then the gradient should only pass to the rest of the network back to the weights to update the weights. Okay, it's like removing the restricting the capacity of the network. Okay, the full network had all the neurons. Now I dropped some of the neurons, like in this case, in this example, I dropped this guy and this guy. Then the rest of the network, which is these weights, these connecting weights, not these guys because these are dropped. These are dropped, right? Some weights here, some weights here, some weights here, and some weights here. The ones circled, they are the only ones who should get updated, and they should be still able to predict the output class correctly. Okay, that's the idea.
So all these tricks will work. It might work for one data set, but not.
This works for many data. These are generalizable tricks, and that's why we are talking about it in the lecture. If they were only specific to a single data set, then we would not be talking about it. Okay. In fact, if it's something works only for a single data set, it's not. Generalizability is a very important aspect of learning and research. Okay, if you do research and you for a single specific data you can do something, that's not enough. It has to be generalizable across domains or and so on. Okay, so it's intuitively regularizing. It's basically saying the smaller capacity network should still predict properly, and it's basically ensuring that all neurons are useful in the sense of all neurons are learning. All weights corresponding to certain neurons, different neurons are learning the patterns, input patterns properly. Okay, it's introducing redundancy into the neural network. Okay, that interpretation is not needed. And one last thing about dropout is so how do you do actually dropout? So let's say think of one hidden layer neural network, 2-layer network. Okay, so you have this. From input X, you do this transformation, do the max ReLU. Okay, then what you do is you drop out. Dropout is drop the nodes we saw in the previous slide, and then compute the remaining. Dropout just means setting them to 0. You compute the remaining thing. Now you can do that during training, but you should not to counter the effect of dropout, because you don't want to drop out in the test time. Okay, because if you drop out, then your prediction is dependent on which neurons you dropped out. So you just have to renormalize by multiplying it with the probability of dropout. So you drop out a neuron with some probability, let's say 10%. So for each neuron, what you do is you flip a coin. If it lands head with some bias, let's say 10%, then you drop it out. Then that probability should also be multiplied to scale the activations properly. Okay, this is just a minor thing, but dropout is essentially a way to regularize, but it's indirect compared to L1 and L2 regularization. Okay, L1 and L2 is just a part of the loss function. It's add an additive term to the loss function. Here it's not the case. Okay, that's the non-trivial part. And so that's any questions about dropout? So in the next few minutes, let's see. Okay, some people are running something, or maybe not. Let's see. So last time I had, I guess, shared this particular notebook, right? So this notebook is, I had asked you to step through this convolutional neural network. So it's a, what is it? Okay, so we'll actually, if time permits, we're going to go through some details of this notebook. But the first thing is this notion of transform. So you can see, so we'll not go into the details right now because we are running short of time. But these transforms, transform.random resize crop, random horizontal flip, those are the data augmentation part of today's lecture. And there's some supporting document here. Okay, so for example, if you want to know how much memory you're using, so I ran it at some point of time, and this is, so you can run actually command line arguments inside the notebook. So NVIDIA-SMI tells you how much memory is being used by your GPU. Okay, so this GPU only has 8 gig memory. So sometimes you'll see memory errors and so on. So you'll have to then reduce batch sizes and things of that nature. We'll see this later. Maybe when you work with CIFAR 10 in your assignment, you will probably come across these issues. Okay, so that's fine. So this script is actually doing the two things that we discussed today: 2 parts of transfer learning, feature extraction, and fine tuning. This script is actually doing that by starting with a network called ResNet 18. Okay, and there are actually ResNet 18, 34, 50. Bigger networks will not fit into the memory, so 18 was chosen here. And and you can see usual things like choosing cross entropy loss as the loss function and so on, and choosing things like SGD. Okay, and I also wanted to show okay, I think yeah, I was trying to see if they explicitly talk about dropout. In this script, maybe not. Okay, I think they're using high level, I guess, function calls to add the fully connected layer at the last part to do their classification task. So the whole point is use the ImageNet pre-trained model, in this case ResNet 18, and do a classification, which is I think in their case it's a 2-class classification problem. So they just change the last layer to a weight matrix which has 2 scores as the output. So it has 2 rows and whatever 1000 dimensions as the columns, and they train that here. Okay, and you can run this very quickly on the GPU machines. Like so they actually train it multiple times. As you know, there are 2 transfer learning approaches, right? So we do it. I mean, you can do it in less than a minute. Okay, so go through this code, and we'll actually probably discuss some of the details of what's happening maybe in subsequent lectures. Okay, that's it for today.